Hey class, this is Mr. Robertson. In this video we'll be looking at problems 83 through 89. The U.S. Census Bureau, where's my glasses? Sorry about that. Takes a census every 10 years. The population in the year 2000 was estimated at 281.4 million people. A model created at the time predicted that the population would grow, population grew by about 2% per year. So, a couple things. I just want to summarize what we know, right, about this. So, first of all, I'm gonna let x be the number of years past the year 2000. So, if x is 1, that's the year 2001. If x is 15, that's 2015. Y is the population in millions of people. So, if you see an answer like 5, right, you know that's 5 million people, not just 5 people. And also the assumption for their model was that it would be the population would continue increasing by 2% each year. So the other thing that's here is they're giving us the zeroth term, right? They're telling us at this year 2000 the population was 281.4 million people. So using that, let's go ahead and write down what we think the model should be. So again, with our definition of x and y, right, y, the population expressed in millions, should be the population at year 0, 281.4 million, times, now we said it was 2% and increasing, so those two things together let us know that our multiplier for this geometric sequence is 1.02. Every year, and that's what x is, every time that x increases by 1 year, that will include all the previous population plus 2% of that previous year. If the Census Bureau had conducted a count in 2005, how many people would it have expected? So if it went out and did another census, how many people would it expect? Well, to answer that question, we're going to use our model, right? So let me go ahead and turn on the calculator, and it's basically just 2 point, no, not 2 point, I'm sorry, it's 281.4, and we're going to multiply, oops, I got that in there twice. We're going to raise that to the power of, no, Roberts, you're getting ahead of yourself. We're going to multiply that times 1.02. I just like the decimals today, 1.02, and I'm going to raise that to the x power. So there we go. So except instead of x, right, what we're going to do here, if I want to know what it is, what does it say in 2005? Well, 2005 is 5 years past 2000. So remember, my definition of what x was, x is how many years past the year 2000. So I'm going to plug in that x is the number 5. So just go back up here and I'll retype a 5 instead of an x, and it gives me that the population predicted would be 310.7 million people. So roughly 310.7, and again these are million people, and that's how many we were projecting for the year 2005. Using the model, how many people would the Census Bureau have expected to count in the year 2010? That's going to be easy to answer, because I'm just going to go up and grab this expression again, and I'm going to evaluate it now, not when x was 5, but I'm going to jump back over and plug in that I want to figure out what it is when x is the number 10. So when x is 10, you can see we're getting 343, I'll leave it as 0.0, right? 343.0, 343.0 million. And you might be asking, why are you putting the 0.0 there? I'm putting it there because it's telling me that I'm correctly rounding to the nearest tenth. So that 0 has some significance. So 343.0 million people. And then the final question says, the actual 2010 census put the population at 309 million people. What is the residual, and what does it mean? So if we recall, residual, right, is always the difference between what was actually recorded and what was predicted by our model. So you can see I've got the value that's predicted by our model right here for 2010. The predicted value was 343 million. The actual value was just 309 million. So my residual is going to be the difference between those two numbers. So the residual is going to be 309 minus 343. And when I do that subtraction problem, why am I doing it with a calculator? Because I can. 309 minus 343. I get that it's negative 34. So this is equal to negative 34 million people. So what does this mean? Well, it means that my model is over predicting population, right? So one of the things that's nice to do with any model is to grab the model and go back and look at what it predicted and then figure out what the actual values were. And you can learn a lot when there's discrepancy between what a model says you should observe and what you're observing. Basically what you learn is that your model needs to be adjusted. There's a problem with the model, and it's not giving you good predictions. So I would say that basically what's happened is the population increase has slowed down. We're not growing at the rate that we thought we would. And I want to try and make sure I write down those things, because I think a good answer would have all these things, right? An answer would have what X is, what Y is, maybe summarizing the fact that you're increasing by 2%. It would include the model, right? It would include the answer to part A and B, what the predicted values were for 2005 and 2010. And then the fact that the residual is negative 34, and then what that means to us. So all of those elements should be kind of in your answer. So I want to make sure I try and keep writing those things down. Let's move on to question number 84. Fun question. I know where this is going, but I'm not going to talk about it a lot. All they're asking us is to take a look at these two systems and see if we can figure out what both A and B are. So let's go ahead and take a look at the first one. What I like about the first equation is very clever, because look at this, b to the 0 power. I know that is the number 1, right? This equals 1. So because of that, I can rewrite this equation as 6 is a. Oh, in other words, a is 6. So I know that a is 6 right off the bat, just because of the fact that b to the 0 power is 1. What I'm going to do with that is I'm going to substitute that value of a into the second equation. So just rewriting the second equation is going to be 24 is equal to 6 times b to the second power. Now dividing both sides of that equation by 6, right, we get that 4 is b squared. And if I want to get rid of the squaring of both sides, there's a missing step I'm not going to put in here, but we'll talk about that more when we're dealing with inequalities and inequalities. Anyways, I digress. But I'm just going to say, look, there are two values that b could be. B could either be positive 4 or it could be negative 4. If you think about it, right, if you take b 4 positive and you square it, oh no, it could be positive or negative 2, my bad. If you take 2 and you square that, you get 4. But also remember, if you take negative 2 and you square that, you also get 4. So b could be either one of those. We've already talked in class about the problems of considering b values that are negative. So I'm just going to say here that we're going to just consider the positive value of b. b is 2. And that's it, right? We've got a solution. B is 2 and A is 6. Let's take a look at part B and see if it's easier or different. So in this one, I can see that I do not have the b to the 0 power, so I'm not going to immediately be able to just figure out what A is like I did in the previous problem. However, I can isolate A in both equations and then use the equal values method. So what my strategy is going to be is I want to get this variable A alone in both equations and then use the equal values method to solve for B. So in the first equation, to get A alone, I'm going to divide by B squared, and as long as B isn't 0, that's not going to be a problem. I guess that's a caveat. In the second equation, I'm going to divide by B cubed, so this is going to become 128 divided by b to the third, and again, as long as a isn't 0, or b isn't 0, that's not a problem. So thinking about, right, the fact that, hey, certainly within the context of this problem, a is equal to itself, and I have not one but two ways of writing a. So on the left hand side, I'm going to use that first version of a. I'm going to write 32 over b squared. And on the right hand side, I'll use that second version of b, 128 divided by b to the third power. So you can see now, right, using equal values, right, a is equal to a, so 32 over b squared has to be the same thing as 128 over b cubed. This is a beautiful time to use fraction busters, right? I could multiply both sides of this by b to the third power. And I like to put the 1 over there because I think sometimes we get confused by that. So I'm going to multiply both sides by b to the third. And you know what? I'll just show that step too. So I'll write 32 times b cubed over b squared. And then I get 128 b cubed over b cubed, which is really super nice, right? Because now clearly the right hand side is just 128, and on the left hand side I've got b cubed over b squared, which is just going to be 32 times b. That's beautiful. So I'm just going to take 128 and divide both sides of, I'm going to divide both sides of that equation by 32. So let me hit divide by 32. And when I divide both sides of that equation by 32, I get that b is the number 4. So we now know one of the values, right? We know what b is. And we have two wonderful ways of figuring out what a is, and it shouldn't matter which one we use, right? Either a is going to be the 32 over b squared, or a is going to be 128 divided by b cubed. So I'll just use the top one. I might use both. 32 divided by 4 to the second power. 32 divided by 16 is 2. You're a genius, Mr. Roberts. And then 128 divided by, it's going to be 4 to the third power. It also produces a 2, right? So I can see undoubtedly that a is 2. So my solution, I found for that system of equations, a is 2 and b is 4. Moving on. It says solve each equation below for the indicated variables. Okay, so first of all we want to be solving for L. So you can see there's the L right here. So for me to solve for L, I would begin by getting rid of the 2w from both sides. So I'm going to subtract 2w's from both sides. So on the one side I get p minus 2w. And on the other side, when I take away 2w, I'm just left with 2 times L. And then finally, to get L alone, I'm going to divide both sides by 2. So it looks like, by 2. So P minus 2 times W, all of that divided by 2 is what L is. So L is P minus 2W, that quantity divided by 2. Next problem, solve for pi. What is pi? We know, right? It's the ratio of circumference over diameter. Well, look, you can see that right here. If I divide both sides of this equation by twice r, right, this side and this side 2r, I get that c divided by 2 times the radius is pi, and of course 2 times the radius is diameter, right? So pi is the ratio of the circumference of a circle divided by twice the radius or the diameter. And then finally part C. You know, I should put boxes around these. Let's a nice green box, right? So here's a nice green box for this problem, and a nice green box for this problem. And now we just got to do part C. It says solve for R. So I want to get R alone. You know, I'm gonna do this, right? There's other ways I could do this, but I'm going to use fraction busters because I understand that. I'm going to multiply both sides by 3. That's going to give me 3 times v. And on the other side, when I multiply that monomial times 3, it's just going to be 4 pi times r to the third power. I'm trying to get r alone, so now I'm going to divide both sides by 4 pi. Okay, so it's going to be 3v. I'm going to divide this side by 4 times pi. And then I'm going to divide the other side also by 4 pi. And you can see when you've got 4 times pi times r cubed, and you divide that by 4 pi, you're left with r to the third power. And then finally, to get r alone, we actually talked about this recently in class. It's kind of a fun trick. If I want to get r alone here, I could raise I'm going to have to do it to both sides, but I could raise this side of the equation to the 1/3 power, right? So when I have a power raised to another power, the rules of or laws of exponents, the shortcut that we've developed, right, is that I can just multiply the 3 times 1/3. Well, 3 times 1/3 is just the number 1. So on this side of the equation, I'm just going to get r to the first. On the other side of the equation, I'm going to get just raised to the 1/3 power. So my answer looks like 3v over 4 pi, all raised to the 1/3 power. And I think we've also discussed this in class too, right? If I have any value x and I'm raising it to the 1/3 power, that's exactly the same as the cubed root of that x, right? So this denominator in this exponent seems to be playing the role of the root index, right? So I could take the cube root and get the same thing. So you can either say that r is 3v over 4 pi to the 1/3 power, or you can say that r is the cubed root of 3v over 4 pi, and that is what r is. That's fun. I mean, it's fun. In fact, it's so much fun, I'm going to put a green box around that. I enjoyed that problem. Okay, let's move on down to question 86. Okay, Coach Ron. I did not, so this is a basketball team, right? So I did not realize that at Shasta High now, track ended up being a sport where we had to cut some players this year. Just too many people tried out for track. It's a thing, right? But anyways, I mentioned that just because we're talking about a basketball team and running, right? So anyways, Coach Ron has 15 athletes trying out for 12 openings on the varsity basketball team. As part of the tryout, he has each player run a mile. And Ron records their time and heart rate as they finish. Coach Ron made a scatter plot as follows. So here's a scatter plot. And it's great because not only are we seeing here the least square regression line, right? The y equals 173 minus 2.0 times x, an equation that attempts to model it. We also see the correlation coefficient. So when you look at that data, I would almost think there was no correlation coefficient. It just seems completely random, right? So if you were trying to come up with some kind of a model that would say, hey, if your time, if you run it in this time, this would be your heartbeat. I don't see this as being a good model for that, right? This is not an efficient model. I don't think this gives me any good information of using the time it takes me to run a mile versus what an anticipated heartbeat would be. All the data is recorded right here. Okay, so question A. And question A, Ron's assistant Cheryl believes they can still find something useful in the results. So, okay, both Ron and Cheryl recognize that a correlation coefficient of negative, whatever it was, negative 0.119 is not a very strong association between the two. She proposes that if heart rates could be considered the level of effort, so how fast your heart's beating is effort. In my case, it would be how out of shape I am. But she's saying, hey, if heart rate could be considered the level of effort given, some athletes might stand out as more or less desirable for the team. Cheryl divides the scatter plot into 4 quadrants and put the new labels on the axis. She labeled each point. And so she also labeled each point. She drew the following scatter plot. Describe the association to Coach Ron in some detail. So here it is. And if I kind of look at some of the extremes on this, like I consider like this person right here. This person, I think probably had the slowest time running the mile out of everyone, right? They were very slow time. However, so if you just draw the line straight down, you can see, right? This is about the amount of time that they took, and if you come over here and just follow it all the way back this way, you can see what their heart rate was, right, when they finished. So if we're saying this is higher heart rates, or like we're using effort to describe what that means, they really put a lot into it. This person right here was all heart, right? This person left nothing on the table, worked really really hard, and still didn't have a great time. But the thing is like people like this that are kind of stubborn and they put a lot of things into it, they tend to get things done in the long run. I'm a cheapskate and I play these crazy games on my phone, and I will never ever pay for like any cheats on the game to make it easier to win. To me, it may take me like 12 times to get past a level, but to me, it's just like I'm so stubborn, and a lot of times I figure things out. It's just like I'm learning things too while I'm stubborn. So, if you're doing your homework and you're struggling, hey, that is where the battle is, right? Putting your heart and soul into it, and leaving nothing on the table. I hope that doing your homework doesn't increase your heart rate. But anyway, so that's maybe a way that you consider that person. If I look at like person O, that person still had a very low time, but look at their effort, right? It's just like, dude, you're not even trying, right? And you could say to yourself, maybe they don't even want to be on the team, or maybe it's just not for them. But for some reason, they haven't kind of connected with this idea that I really want to put a lot into it. And then there's other extremes, right? Like we can look at person D, and I don't know, maybe E or F, and an O, or I could look at person F. F is like a lot of effort, and wow, that person performed pretty well. D, they performed well and they didn't even put a lot of effort into it. So, so what would I tell coach? I don't know, coach. I don't know. But is there? So it says describe the association to Coach Ron in detail. Let's see. I gotta say something to Coach Ron about these values. So these are some of the answers that the textbook had, and I just share them with you. Obviously, answers vary. And if you're in a situation with a study team or individually and you're writing a response, think about these and try to think about how you could construct responses like this to yourself. So for D, player D, we might say ran fast, but seems to give a little effort. This athlete already might be in outstanding physical condition, or perhaps have an attitude problem. So again, if you're looking at player D, they're right here. Not a lot of effort. Maybe maybe if they would have given a little bit more, they could have literally been the fastest player. They could have beat player A, who was at the top there. For player F, strong runner and a strong effort. I recommend keeping this player. So good effort and good outcome. So they're up in that upper left quadrant. O ran slowly and gave little effort, along with players M and N. You can see they were all down in this little group right here. We don't know these players' potential or their motivation level. Maybe we should cut them. And then the last one is P. P was the slowest of the group, but with the highest effort. This player may improve over time and perhaps could serve as a role model for other players on the benefits of strong effort. So anyways, these are just recommendations. I'm glad I'm not a coach, especially thinking. I know that coaches really work hard on deciding who's on the team and who's not, and it's never a fun thing to do. So I'm glad I don't have to do that job. All right, let's move on to the next question. Here we go. 87. It says the drama club found the best price for renting a fog machine was $38 for every 3 days, plus a one-time $60 delivery fee. Make a step function that shows the cost of renting Ooh, the fog machine. Okay, so let's already I'm thinking, well, we're gonna do a graph, so let's just kind of get quick on this. So let me grab a ruler, and I'm just gonna slam down a horizontal axis with this pen, and let me go 90 degrees and get a vertical axis. 90 degrees would be nice, thank you. Right, and I don't think I need the ruler anymore. Let me get rid of that. So just kind of broadly, right, this is, I'm going to say this is $0 down here, and then these are going to be the number of dollars for rental, and this is going to be days. My x value will be days. And what does it say? It says for every 3 days. So every 3 days the price jumps up. So I could make this like, okay, here's 3 days, and then here's 6 days, and then here's 9, and then here's 12, and here's 15 days. What do they say? It says for up to 3 weeks. 3 weeks is 21 days. I'm going to stop at 18. You rebel. And then as far as cost goes, I know that my initial cost is going to be, let's see, it's going to be $60 plus 38. So it's really close to $100. So if I was to say, I don't know, how I want to scale this. I could say that this is, I could say this is 100. That would be 50 then. That's 100. This is 150, 200, 250, 300, 350, 400 maybe, 100, 200, 300, and again these are dollars. So if I rented it for just 3 days, first of all, I'm going to start with an open circle. I don't like that. I got this big line here. Let me make it a clean line. I'm going to start with an open circle here, because if I'm renting it for no days, I'm not paying anything, right? So I'm not paying anything for that. But if I rent it for up to 3 days, and including 3 days, right? So that's why I'm putting a solid dot here. The price I pay is this horizontal line. They asked me to make a step function, so this is what it's look like. So from no days, but not including the no days, up to 3 days, I'm paying $60 plus 38, right? Now I need to add another $38, which is about another 40ish, right, close to 40. So for the next group of days, somewhere below the 150, like in here, it's going to be an open dot, because what do you pay for 3 days? You pay the bottom dot, this one, right? But from 3 days onward, up to and including the 6th day, right, and including the 6th day, so I got a solid dot here. This is what you would pay. You would pay, what is it, 98 plus 38. And then 98 plus 38 plus another 38 would be somewhere, I know it's quite a bit less than 200, but just somewhere, again, just jumping up, and it's going to be that for the next 3 days, and then this would be a solid dot. So this is what the step function looks like, right? And just remember what these dots mean, right? This open circle means it's not included. So that's not a point that's on the graph, it's just kind of a boundary. And the solid dots mean they are included. So if you were to ask me what do I pay for 6 days, I would not go to here. This is not where I would go. I would go to this dot, and I would say, oh, you're going to pay whatever this price is, which is 98 plus 38, just a number. So anyways, just continue those lines out, and that's the step function. Next, it says on graph paper draw AC, where A is at 2.6 and C is at 5.1. Well, I think I've got this graph set up. Getting this right is important, because a lot of times I'll get the wrong point down and it changes it. So A is at 2.6, X is 2, Y is 6. Let me put this is point A, and this is 2 comma 6. And point C, does it say C? Was the other point C? C, so 2.6, and C is at 5.1. Okay, so 5.1. So I'll go over 5 and then down to -1. Whoops. Do I not have the pen on? There we go. 5. Something's not working. Come on. Okay, now it's working. So I've got that A was at 2, 6, and C is at 5, negative 1. So two questions. We're considering segment AC, and they're asking us to find the location of the midpoint of segment AC and also figure out how long segment AC is. Finding the equation for AC is pretty easy for us at this point. So if I look at just traveling along this vertical line from A all the way down to the vertical line that C's on, I can see that this line segment is 6 plus 1 or 7 units long, right? And I could get that with an arithmetic problem. I could say, look, the y value at A is 6, and I'm going to subtract from that the y value at C, which is negative 1, and 6 minus negative 1 is 6, not 6 plus 7, it's 6 plus 1, which is 7. So that's a change of 7. And horizontally, I'm going from an x value of 2 at A to an x value of 5 at C. So that changes by 3 units. So if I'm going to figure out the location of the midpoint, I could figure out the location of the midpoint by considering half of those distances. So instead of traveling half, I could literally just go down 3.5. So if I went down the 1, 2, 3, and then a half, right? This value right here is going to be the y value for my midpoint. And you can see I can go up 1, 2, 3 and a half also. So that's the midpoint. That's the y value at the midpoint. Let me write it down. 3.5 is the y value at the midpoint. And then the x value, instead of traveling 3, I can just travel 1.5. So 2 plus 1 plus a half would be 3.5. Oh, they're both at 3.5. Really? It doesn't seem right to me. 3.5. So I'm claiming that is the midpoint. So another way that we could, let me draw that line. See if it is. I'm always suspicious of my work. With good reason, I make mistakes. So I think that's the location of the midpoint. Another thing that you can do, and I've heard some of you say this, is you can average the x value. So for example, if I take the x value at A and I add to that the x value at C, I get 7, and then when I take half of that, I do get 3.5. Same thing with the y values, right? Y at A is 6, and if I add to that the y at C, which is negative 1, I get 5, and half of that, no. What? 6 is 5. Well, you can see the benefit of like questioning yourself, because clearly I made a mistake here. When I add 6 and negative 1, I definitely get the number 5. Got it? And 5 divided by 2 is not the 3.5 I thought it should be. 5 divided by 2 is 2.5. And what's nice about that is I can see now, looking at the graph, that's exactly what it should be, right? If I look at the average of those, I should be hitting 2.5, not 3.5, and that's where this point is. So the problem was not 6 plus negative 1 is 5 divided by 2 is 2.5. The problem was that I didn't read this right. So this should live at, the y value should be 2.5. And for those of you that were screaming at your computer screen, thank you. I think I heard you. So the location of my midpoint is at 3.5 comma 2.5. X is at 3.5, Y is at 2.5. And then the other question is, how far is it from A to C if I was to travel from A to C? What's nice about having this slope triangle all set up is that I can see the length of the two legs of this right triangle. And if I just solve this right triangle, it'll give me the length AC. So this, right, notationally, that means the length of segment AC. So this is segment AC. This would be line AC. Actually, that's ray AC, right? And this would be line AC if arrows are both ways. This is the length of segment AC. So that's what I want. Well, if I take the leg 7, square it, and add to that the other leg 3 squared, I get the length of AC squared. So let me square 7, it's at 49, plus another 9, looks like 58. is the length of AC squared, and then AC would be the square root of that, right? Root 58 is AC, and I don't think that that's got, I know 58 is clearly divisible by 2, and this is not a requirement of this problem, but I like looking at these. 29 I cannot divide by 2. 29 is prime, so I am stuck with root 58 as my answer. So the length of segment AC is the square root of 58. And finally, we are on to our last problem in the set, question 89. Here it is. It says 89, it says determine which of the following equations are true for all values, always true. Okay. For those that are not, decide whether they are true for certain values, sometimes true, or not true for any values, never true. Justify your decisions clearly. So look, if I look at part A, I'm making a claim that x minus 5, that quantity squared, is always the same thing as x squared plus 25 squared. And I think we've discussed this enough, and I know I did it last year. I talked about this in terms of my puppy Fen, but what does it look like when I square this binomial, right? Remember, to square a binomial means that you're going to multiply that binomial exactly times itself. Writing that expression like this might help you make the mistake that I see many students making, where they incorrectly assume that they could just square the two terms independently, slam them together, and get the product, and it's not that case. I always encourage you to just take a moment and look at an area model to help clarify this. So if I look at an area model, we could have a length of, let's see, this length I'll say is x units long, and this right here is -5, and then so that's that one of them, and then the other way, this is an x units long, and this would be a -5. So there's 4 parts that come in play into this product, right? It's not just squaring the binomials. This first part, x times x is x squared. This is a minus or -5x. Down here I've got a -5 times an x, right? Remember, the area of a rectangle is just its length, -5 times width 5, so this is also -5x. And then finally I've got the -5 times the -5, which gives me the positive 25. So when I do that, I can see what I actually get is x squared minus 10x, and then a plus 25. So that thing that I just got, these two things that I'm highlighting with this yellowish pen, those two things are equivalent. This is not the same as it, right? Those x minus 5 quantity squared is not the same as x squared plus 25. Now, however, that means that that's not always true. I can pick a lot of values of x, or if I plugged it into my calculator both ways, they would give me different things. However, that doesn't mean that it's never true, because with one, maybe it's the only value that I can think of, when x is 0, I end up getting on the left hand side -5 squared, which is 25, and on the right hand side, if x is 0, that's just 25. So it is true when x is 0, but other than that, those two things are not always equivalent to each other. Since we're here at C, let's just go ahead and do this. If I was to simplify the left hand side, I can see it's got a giant one there. I could write this as going to be 2x squared times, I'll just write the y squared and then times another y. So if you're wondering what I did, I just rewrote y cubed. Y cubed is the same thing as y squared times y, and I did that because in my denominator I have a y squared, and when I look at that and I see this giant one, right, I can say, oh, look at this, those are the same. So what this simplifies to is simply 2x squared times y, which is exactly what we had on the other side. So these are going to always be the same, right? It doesn't matter what I pick for x and y. If I square the x, multiply by 2, and then multiply by the y I selected, I'm going to get the same thing both times. So those are always going to be the same. Let's look at B. Okay, so B, perhaps, right? At least let's go ahead and look at this as an area model. So I'm just going to quickly sketch a little rectangle, or I made it maybe look more like a square. So I'm going to call this 2x, and then I've got a negative 1. So if you look at it, I've got this quantity 2x that's being modeled by this length, and then I've got a minus 1, and then I've got this quantity, I'm calling it x, and this is by 4. Again, these are called generic area models because clearly these are not showing the relative lengths of any of these things. It's just giving me a place to look at the 4 different things that go into this product. 2x times x is 2x squared, which is what I've got over here. Then I've got a negative x, that's negative 1 times x is negative x, and I've also got a 4 times a 2x, which is an 8x, and if I combine those, right, a negative x and an 8x, that is 7x, so that's the same. And then the final one there is, this is negative 1 high by 4, so this is a negative 4, and that's the same also. So this is, the left and the right hand sides are the same here as well. Regardless of what I pick for x, it's always the case that 2x minus 1 times x plus 4 is always identical to 2x squared plus 7x minus 4. And then the final one that I have is this, and I'm still going to look at this with an area model. So I've got my beautiful little rectangle here. I'm going to call this 3x. This would be a negative 2. So that's the 3x and the negative 2. Along the bottom I've got a 2x, and then I've got a plus 1. And the pieces that I have here is this is 3x high by 2x wide, so this is 6 times x squared. X times x is x squared. This is negative 2 high by 2x, so this is negative 4x. This is negative 2 by 1, and then this is 3x by 1, which would be 3x. If I combine these, I do get 6x squared, and when I combine the negative 4 x with the 3x, I do get a negative x, negative x. But then where it differs is that this is a negative 2, right? And I can see up here I had a negative 5. So again, I think this would work. No, if x was 0, it wouldn't work either, would it? I don't think this would work. One of the things I could do if I'm really curious about it, and why not, right? What else am I going to do with my time? If I clear this, actually I think I already did it. Yes, I did. Look at this. I've got 3x minus 2 times 2x plus 1. That's the left hand side. And then I've got the right hand side, 6x squared minus x minus 5. And if I go ahead and graph both of those, I changed the window so I can see it. And you can see these graphs are not touching each other. And I just have to think that it's going to continue to be the case that they're just going to get maybe closer and closer to each other as x's get large or x's get really small. But I don't think that they'll ever touch each other. There's not going to be a spot that they share. I guess we could solve this as an I could solve this as an equation. I could prove this to myself. I could write the other side as 6x squared minus x minus 5. So if I take away 6x squared from both sides, I get negative x minus 2. And over here I get negative x minus 5. So again, all I did was I took away 6x squared from both sides. Now I'm going to add x to both sides, and I get this goofy statement, right? I get negative 2 is the same thing as negative 2 is the same thing as negative 5, to which I say, what? That ain't true. So actually it's very clear to me that there's no solution. There's never going to be a point when those two things are equal to each other. I can kind of see that on the graph, but algebraically I'm more convinced of that argument. So anyways, that's the end of this homework. I hope you found this useful. Remember, the goal, guys, is for you to get mathematically strong. So get strong, and I'll see you in class.